Hello and welcome to section 5. In this section, we are going to cover clustering techniques, which are the second category of unsupervised learning after dimensionality reduction that we covered in the last section. So let's get started. In this video, we are going to introduce clustering and k-means clustering. Specifically, we are going to introduce ourselves to clustering, what clustering is. We are going to look at some use cases and applications of clustering. And we are also going to describe k-means clustering, which is one of the popular algorithms of clustering. The basic idea behind clustering is to group data by identifying hidden similarities between samples in a dataset. Clustering techniques mostly use some form of distance measure to identify those similarities between samples. It is used in many applications, real-world practical applications, and across many domains. So let's discuss some applications of clustering. One of the applications is segmenting customers by purchase history. So there could be similarities between different customers and we want to segment them or group them or cluster them based on what they have bought in the past, right? Similar products, similar items, similar tastes in products, similar behavior and all that. We could segment or cluster users by their actions and activities on specific websites, e-commerce platforms, other platforms, and also applications. How they use applications, what kind of activities they do most frequently on websites and while using the applications. We may be able to define user profiles based on similar interests that the users might have for websites and for mobile users or other application users. Profile building is a very common activity in many social media platforms and websites. We could group products themselves by their sales activity, seasonality in selling of products based on discounts or sales that were going on, and so on. So we could group the different products. Remember, in unsupervised learning, we don't have any labels or any targets, so we are not really classifying. We could think about grouping images and videos based on their similarity. Cluster the images based on the type of faces or type of things or type of clothes and type of items they're showing. And similarly, we could do it for the videos as well. We could identify topics of videos and so on. We could imagine identifying groups in healthcare, like for example, people who have specific eating habits, trends to care about their health based on their exercise routines and so on. We could think about anomaly detection, like what is deviating from normal. For example, separating valid activity users from bots on websites. And we could think about identifying fraudulent transactions while buying and selling online using credit cards and debit cards. This is also an application of anomaly detection, and it is a very important application. We could identify fraudulent transactions in insurance, in credit cards, and so on. So as you can imagine, there are a lot of applications where we need to group and cluster things, people, and items and products, etc. based on some kind of similarity they exhibit. K-means clustering is a widely used simple algorithm. The main property of this algorithm is that the parameter k, which is our demand from the algorithm to divide the dataset into k number of clusters. In other words, we set the parameters so that we are telling the algorithm, please cluster these users into 7 groups, for example. Another option could be that the algorithm itself decides how many groups it's going to find from the data on its own. In this case, we are telling it that we want 7 groups or k clusters. The idea in k-means clustering is that samples near each other in terms of distance should be grouped together. It's a very simple idea, and it's basically the same idea in most clustering algorithms. These groups are called clusters. Euclidean distance is mostly used to estimate clusters. Let's look at the algorithm in a bit more detail. First, we generate k cluster centers, also called centroids, either by randomly selecting a sample from the dataset or generating random numbers. We assign each data sample to one of these k clusters using Euclidean distance, that is, a sample goes to its nearest cluster or nearest centroid. We recompute the centroid of each cluster by calculating the mean of each cluster. If the cluster centers or centroids don't move after step 3, we terminate. So we have final clusters already. Else we go to step 2. We assign each data sample to the clusters again, and then we recompute the centroids again and see if they change now, until we have converged and there is no change in the cluster centers. So let's look at a simplified example of this algorithm. So first, let's look at a graphical illustration. So we have these data points in two-dimensional space. Let's say we have two features, X and Y, and these are our data points plotted in a two-dimensional space. From these data points, we randomly select 3 points as cluster centers. So we have a red point, a green point, a blue point. We say we have 3 groups, already have, just randomly. So whatever XY coordinates these 2 points have, they will become the cluster centers. Next, what we do is we assign each of the other points. So basically these 3 points go into their own cluster because they are the ones. The other option is we could have selected any points at random. Could have generated centroids at random, but we didn't do that. In this case, we selected centroids from the data points themselves. So here we have assigned these 4 points to this red cluster because they were nearest in terms of Euclidean distance from this centroid, and we have assigned this green point, this one, to this cluster, and all these 4 points, 1, 2, 3, and this one, to this cluster. So we have formed 3 clusters, and then we calculate the mean value of each cluster. So we just add up all these X coordinates and divide them by the number of points in the cluster, and then we add up these Y coordinates and calculate these 2 means of X and Y, and that forms our new centroid for this red cluster, and similarly for the green case and for the blue case. So if those means result in centroids or center of clusters which were different from the previous iteration, then we have to repeat, and we have to again assign all the data points to these new centroids by calculating the Euclidean distance and assigning them to one of the clusters. So some of the points might actually move from one cluster to the other in our each iteration. Here is a simplified illustration with numbers. So suppose we have these data points, and let's say k is equal to 2. So we want to divide these data into 2 clusters. So we randomly choose 1, 4 and 4, 2 as our centroids. So obviously 1, 4 goes into its own cluster, and 1, 2 and 2, 3 based on the Euclidean distance are in this cluster 1, and the other points are in the 4, 2 cluster. Now we calculate the mean of cluster 1, which is going to be 1 plus 1 plus 2 here, divided by 3. Y is 2 plus 4 plus 3 divided by 3. So it is 1.33, and 3 is going to be the new cluster centroid for cluster 1, and the new cluster centroid for cluster 2 is going to be 4 and 2.4 similarly. So obviously these 4 and 2.4 and 1.33 and 3 are different from 1, 4 and 4, 2. So we will repeat and again calculate the Euclidean distance of each point from these new centroids, and so on. Now there could be some improvements in speeding up the convergence of k-means. In most cases, the shifting of centroids by bigger margins close to their final position occurs during the first few iterations. And this is an observation after a lot of experimentation with the hundreds of thousands of datasets. Centroids move barely or very slow during the final iterations. A common approach to optimization is to use a threshold for centroid movement. So for example, you could say if they move less than a threshold value in an iteration, the clusters are good enough that we have at that point. Another approach would be to terminate the algorithm when less than 1% of the points change their cluster membership. Sometimes, depending upon the dataset, the algorithm has a hard time converging. In those cases, we may limit the number of iterations to a maximum as well. So either we could limit the number of iterations, and we could also limit the number of points that move from the clusters, and we also could set a threshold for the change in the percentage of change or some amount of change, magnitude of change in the cluster centers. So all these measures would make the algorithm converge better and faster. So this was all about the k-means algorithm.